Hey there, and welcome to The Explainer. Today, we're going to talk about something that's literally powering your life right now, electrochemistry. It's the amazing science that turns chemical reactions into the electricity in your phone, your car, you name it. So, let's get into it. Okay, so here's our game plan. First, we'll unpack how electricity can even move through a liquid. Then, we're going to build a basic cell, piece by piece. After that, we'll look at the two main kinds of cells, figure out how to measure their power, and finally, connect all of this to the raw energy stored in chemical bonds. So yeah, that little battery powering your device, have you ever really stopped to think about what's going on inside it? It feels like magic, but it's not. It's just a really clever, controlled chemical reaction. And today, we're going to pull back the curtain and see exactly how it works. All right, first things first. We all get that electricity zips through metal wires. No problem. But for a battery to work, that charge also has to travel through a liquid. So how on earth does that happen? Okay, this slide really gets to the heart of it. You've got two totally different ways electricity can move. On one hand, you have a wire. Think of that as a smooth, fast-flowing river of electrons. Simple. But inside a battery's liquid, it's completely different. It's more like a bucket brigade. Instead of tiny electrons flowing freely, you have these bigger charged particles called ions that have to physically swim through the solution, passing the charge along. It's a much more hands-on process. So how well does that bucket brigade work? Well, there's a name for that. It's called conductivity. To put it simply, if you have high conductivity, it means those ions are moving fast and easy, and you can get a really strong current. Low conductivity, well, that bucket brigade is moving pretty slow. And here is just a little bit of the lingo scientists use. You'll hear about resistivity, which is exactly what it sounds like, how much a solution resists the flow. Conductivity is just the opposite of that, how well it conducts. And molar conductivity, that just gets a little more specific. It ties the conductivity to exactly how much stuff you've dissolved in the solution. Okay, section 2. Now that we've got the basics of how charge moves in a liquid, let's actually build one of these things. Let's put together the engine of electrochemistry, the cell. You know, it sounds complicated, but building a basic cell really just comes down to 3 essential parts. First, you need 2 pieces of metal. We call those the electrodes. Second, you need that special liquid, the electrolyte, that lets the ions do their bucket brigade thing. And third, you just connect the 2 electrodes with a wire on the outside. And that's it. Electrons flow through the wire, ions flow through the liquid. You've got yourself an electrochemical cell. So we've got our cell. But here's the interesting part. They come in 2 main flavors, and they're basically opposites of each other. And the big difference, the thing that separates them, boils down to one simple question. Does the chemical reaction happen all on its own, or do we have to force it to happen? A galvanic cell is like a disposable battery. It taps into a reaction that wants to happen and gives us electricity. An electrolytic cell, on the other hand, is what's happening when you recharge that battery. You're using electricity to force a reaction to run backwards. So let's talk about galvanic cells. Honestly, just think of your everyday battery. That's what this is. It's got a chemical reaction inside that's spontaneous. It naturally wants to happen. It's like a rock rolling downhill, and we're just harnessing that energy as it goes, turning it into electrical current. And then you've got the flip side, electrolytic cells. This is the uphill battle. This is you plugging your phone into the wall. You're using power from the outlet to force that chemical reaction to run in reverse, to push that rock back up the hill. You're not getting energy out, you're putting energy in to store it for later. Which leads us to a really important question. If a galvanic cell makes power, how much power? How do we actually figure out the voltage we're going to get from it? Well, to make things fair, scientists needed a starting point, right? A baseline. That's what the standard cell potential is. You can think of it as the textbook voltage for a cell, the power it would produce under perfect, pristine, standardized lab conditions. It's our ideal starting point. But here's the thing. The real world is messy. Our batteries aren't sitting in a perfect lab. The temperature changes, the chemicals get used up. It's chaotic. And that's where this incredibly powerful tool comes into play, the Nernst equation. The Nernst equation is basically a reality check. It's brilliant. It takes that perfect textbook voltage and then it adjusts it. It says, okay, but what's the actual temperature right now? What are the real concentrations of the chemicals? And by plugging in those real-world numbers, it spits out the true functional voltage you're getting from that cell in that exact moment. And this is where it all clicks together, our final section. That voltage we've been measuring, it's not just some abstract electrical number. It's a direct peek into the raw, fundamental chemical energy that's driving this entire system. Seriously, if you take one thing away from all this, let it be this. When you look at a battery's voltage, you are literally looking at the raw power, the driving force of a chemical reaction. A higher voltage means there's a stronger chemical push, making that reaction happen. They're not just related, they're two sides of the very same coin. And this chart just lays it all out so beautifully. It shows how three different scientific concepts are really just telling the same story from different angles. You start at the top with a high electrical potential. Well, what does that mean? It means the reaction has a really strong drive. And that strong drive is what scientists call a very negative Gibbs energy, the thing in the middle. And if a reaction has a super strong drive, well, then it's going to run almost completely to the end, which gives you a huge equilibrium constant, the term at the bottom. See? They all describe the same thing, how much a reaction really wants to happen. So why does any of this matter? Well, because this fundamental link between chemistry and electricity isn't just about the AA battery in your remote. It's the key to everything, to fuel cells, to making materials, to the entire future of how we store energy. We understand the how. The only real question left is what